going to get started. We are going to finish chapter 16 today, start chapter 17, which is a short chapter. I want to start chapter 18 just as soon as I possibly can, because it's a long chapter, it's a difficult chapter. That's my plan, because we have a Monday final, unfortunately. And so I want to get done as soon as we can. I'm planning to have a review on Friday night. I don't know what the time is yet. Yeah, next Friday. Yeah, I forgot to submit a room request already, which could be a problem. So we'll hope. I'm going to do it today. Any questions? All right. All right, so we're talking about how to predict the right stereochemistry, the endo product for acyclic dienes. And so what we said is that outside substituents on the diene. On the dienophile, there are no outside or inside. So we're only talking about the diene when we're talking about outside substituents. So outside substituents right here. That's outside, the two hydrogens are in the inside. So I'll label those in just a minute. So outside substituents and the electron withdrawing group on the dienophile are all on the same side. So you could have them all dashed like I have here, or you could have them all wedged. Both of those will give you the correct answer. All right, so I chose them going back. Let me label here. These are the inside ones. Let's do, those are inside. Inside substituents. All right. So let's look at this one here. We've got a methyl on the two ends here. So we want the outside substituents, so a methyl and a hydrogen, and the electron withdrawing group are all going to be drawn going back. Again, if you draw them forward, that's also correct. That's going to go back, that's going to go back. So here's our product. This methyl's going back. This aldehyde's going back, and the hydrogen's going back. So we need to throw on our methyl here. So we're going to have that plus the enantiomer. Okay, so it makes it easy to draw, what is pretty complicated stereochemistry. It makes it much easier to draw the correct product. I just want to show you that the enantiomer has the opposite relative orientation. And so I'm going to redraw the product that I just drew. So I want you to see what the enantiomer looks like. There's two ways we can draw the enantiomer. So I'm going to redraw this. Let's go ahead and leave the hydrogen off because that's understood. But certainly on sapling, you don't want to leave the hydrogen off. So that's the product that we drew there. The enantiomer is the mirror image, so let's draw a mirror image right here. So I'm going to draw this exact reflection in the mirror here. Okay, everybody agreed that's the mirror image? So that's what this is the enantiomer drawn using mirror image. And that is certainly one perfectly good way to draw the enantiomer. I'm going to flip over the enantiomer. You don't have to be able to do this flip in your head. I'm just going to show you what the flip looks like. But if you can imagine, if the double bond right here was the spine of a book, and you have your book open, and this is on the left-hand side, and all we're going to do is like as if we're turning the page. I'm just going to go like this, and I'm going to flip that over. I'm going to flip that over and draw that. So here's my spine now. The spine of our book right here. When I flip that over, everything that is coming up is now going to be going back. So for example, here's the laser pen. I have, let's see, the methyl on the bottom is coming up. And when I flip that, now the methyl's going back. So I'm going to put those on opposite sides. So this is, this methyl will be coming up now. This methyl will be going back. That's also the enantiomer. So that's the enantiomer made by one of two, well, there's three ways to make the enantiomer. Draw the mirror image and flip it like we just did. Or here's your one enantiomer, and to draw this enantiomer, we flip the stereochemistry at every single carbon. Okay, so this methyl would be going back, now it's coming forward. This is going back, now it's coming forward. The methyl's coming straight up, and this is going back. The other way this is the enantiomer is by this right here. Outside substituents on the diene, electron withdrawing group on the diene are on the same side in the ring in the product. I choose them going back. If you choose them going forward, this is what you would draw. So if you choose them all going forward, then that's the enantiomer. So you can get it three different ways. On my test, you will draw one of the enantiomers, and then you can just write plus E. I won't have you go through this whole thing. But I wanted to kind of prove that to you, that is inside substituents, and electron withdrawing group going back. All right, so very elaborate stereochemistry for the Diels-Alder. That's why it's such a valuable reaction, because it's very, very stereoselective. Now, there's one other thing that we have not talked about that we have to consider when we're drawing Diels-Alder products, and that is regiochemistry. And we've kind of avoided the issue. You probably didn't even notice, but it's an important issue. Question? Say that, where? Inside substituent, oh yeah, I did make a mistake on that. This is outside substituents, thank you. Yeah. So yeah, go fix that. Okay, thank you for pointing that out. All right, so regioselectivity is on the next page. The Diels-Alder reaction is regioselective with unsymmetrical dienes and dienophiles. There are two possible orientations. Yes?
I'm sorry, are you talking about the enantiomer? So in this rendering, is it that the inside are going back? Or that the inside is going back to EWG?
Or coming for, oh gosh darn it. You know what? Yeah, coming forward. I have that completely backwards. Let's erase it. Doesn't that look better? Outside substituent electron withdrawing group going forward. Okay, we're nav, thank you. My gosh. Forward, yes. You've saved me a bunch of emails. Thank you. Both of you. Okay, we got that right now. All right, now we're ready to talk about regiochemistry. All right, so I have EDG for electron donating group and EWG for electron withdrawing group. And you can imagine that we have, if we have EDG and EWG here, there's actually two possible orientations. Okay, so we can have the orientation, and I'm not even going to show stereochemistry here because what I want to do is I want to focus on regiochemistry here, so I'm not going to do stereochemistry. We'll come back and do stereochemistry. So if we react like that, I'm just looking right now at the relationship between the electron withdrawing group and the electron donating group. If they react like that, that's what you would get. Now, but they also, you can imagine, and I'll scroll up a little and draw it up here, you can imagine that I could also orient the dienophile in the opposite way. So here would be EDG. I could actually go like this. Right? I could orient that, I could flip that and orient it that way. If I do that, then I get this product. And that's really important because we only actually get one of those two products. Let me show you another example here where the electron donating group is actually on the middle, one of the middle carbons. We can orient that also two ways. So EDG here and EWG here. Or, once again, we can flip the dienophile. If we flip the dienophile, then this would be our product. So two possible products here, we only get one of them. So how do we know which one we get? And that leads us into the ortho-para rule. Now, ortho-para is a new terminology that we're not going to talk that we'll talk about in chapter 17. And so ortho is, and we get this nomenclature from aromatic chemistry. So if we have a benzene ring, there's two if we have two substituents, that would be one possible arrangement. This would be another possible arrangement. And then this would be, oh, I have them drawn right here, so why am I even drawing those? Okay. Doggone it, I'm off today. Let's try that again. I am very off today. Okay, so nomenclature comes from benzene chemistry. Look at the relationship between these guys here. This is a 1-2 relationship. This is a 1-2-3-4 relationship, and this is a 1-2-3 relationship. So when it's a 1-2 relationship on a benzene ring, we call this ortho. When it's a 1-4 relationship, we call it para. And when it's a 1-3 relationship, we call that meta. And so we're borrowing from this nomenclature for benzene chemistry and saying that, calling this the ortho-para rule. The substituents end up on a 1-2 or 1-4 relationship on the 6-membered ring, so that the electron donating group and the electron withdrawing group are either ortho or para to each other. So it's the ortho-para rule. So let's see, and we're not numbering like we're going to name it, we're just looking at the relationship in here. Can you see that that's a 1-2 relationship between the carbons that those electron donating groups and electron withdrawing groups are attached? So this is ortho, and that's the one we get. This would be 1-2-3. We don't get any of that. This would be meta. So no meta. This would be 1-2-3-4, and again, it doesn't matter which direction you number. This is para. That's the one we'll get. This is 1-2-3. This is meta. We do not get meta. So questions on regiochemistry. So that's another factor that we're going to have to consider. Yes?
Do we have to worry about products?
Getting what?
Products, or on the same carbon?
No, you won't get that. Nope. Yeah, up at the top. It's a complicated explanation that I'm not going to have you guys know. And so, but if you're curious about it, you can come up and ask me. Okay, so it's just something you're going to have to remember. I can explain it, but I don't have time. We'll run out of time to cover chapter 18, and I know you won't be happy with me then if I do that. All right. It has to do with the polarity of the two, the diene and the dienophile and the diene. It has to do with how they orientation, or how they orient depends on the polarity of the bonds that are involved and the groups involved. All right, so synthesis using Diels-Alder reaction, predict the product in the following reaction. And what we're going to go ahead and do to make this a little bit better is we're going to put a methyl group on the end here. So go ahead and throw a methyl group on the end of this problem. That'll make it more a reflection of what you'll see on the final, which is what we want to be ready for. And the way that I do this is I do regiochemistry first. Then I do stereochemistry. I know we covered stereochemistry first and then regiochemistry, but when I'm predicting a product, I do regiochemistry first, and then I do stereochemistry. So regiochemistry here. So they can orient this way, or let me draw the other way we can orient these two groups. I'm going to keep this here. I'm keeping the diene in the same orientation, and now I'm just going to flip the dienophile up. One of these two is correct, one of them is not. All right, so then and in order to figure out which one I get, I'm going to connect the two ends and I'm going to number. So this is where our new sigma bond is going to be. So I don't even need to draw the product here to do this regiochemistry, because that's where our new sigma bond is going to be, right where that dotted line is. And what I want to do is I want to do the electron donating group on the diene and the electron withdrawing group on the dienophile. The diene has two electron donating groups. Which one is stronger? This is stronger because it has lone pairs. Okay, this one is stronger because it has lone pairs, so that's the one that's going to determine the outcome. This is the stronger electron donating group. We'll see that again in chapter 18. So by the time we get to through chapter 18, you'll definitely be able to know that that's the stronger one right away. So that's our stronger electron donating group, and that over here is our electron withdrawing group. What's the relationship? 1, 2, 3, 4. That's what it would look like there. That's good, that's para, right? Over here, this would be 1, 2, 3. That's meta. We're not going to get meta. Okay, so that's the regiochemistry. Now we need to do stereochemistry. All right, stereochemistry says, our rule is the outside substituents and the electron withdrawing group are on the same side in the ring. So here's our outside. We don't really have inside, well, we have a hydrogen outside, but there's two hydrogens here, so we don't even need to worry about that carbon because it's got two hydrogens. And our electron withdrawing group are on the same side. Is methyl electron withdrawing group? Methyl's not an electron withdrawing group. So it's the electron withdrawing group that has the p orbitals that tucks up underneath to give the secondary interaction. So those need to be on the same side. All right, so our product is, let's draw it. Methyl going back. Electron withdrawing group going back. What about the methyl on the dienophile? Is that up or down? It's up. Why is it up? Because it's trans. It's opposite on opposite sides of that, so we don't want to change that stereochemistry. So we're going to have this. And then we take a look at that. Is that chiral? It's chiral, so we will write plus E. So there's stereochemistry. Questions? Anybody? Yes? Which CH3? This one? This one right here? If this methyl was cis here, then it would be, I'm going back also here. Yes. All right. All right, so expect to see one like that on the final. One, maybe two, we'll see. Guaranteed. All right, so this one here is a little bit different because it's asking for what diene and dienophile are needed to make the following product. That's a little harder, isn't it, in some ways? So steps, draw the 3 arrows around the ring starting with the pi bond. You can go clockwise or counterclockwise. I don't know why I always do counterclockwise. I don't know what that means. I'm sure that means something about me. Maybe that I'm right-handed or something. But I always seem to go counterclockwise there. All right, so that is going to tell us where the electrons are going. And I'm going to use it can be made from a retrosynthetic arrow. So as you can see, we're going to be breaking this pi bond this sigma bond right here, because those electrons are going to make a new double bond here. These electrons on this pi bond are moving over, so now there's going to be a double bond there. We're breaking this one right here, and then there's going to be a double bond there because there's already a sigma bond, and we're adding another pair of electrons there. So that's going to be a sigma bond. So let's draw our skeleton, and then we'll look at where we could get the correct stereochemistry. So here's our diene. Here's our dienophile. So notice that on our dienophile, this group and this group are on opposite sides. That means that they'll have to be trans to each other on the dienophile. So here's the dienophile. They're trans. Has to be, because they're on opposite sides here. All right, also notice the orientation between the deuterium and the electron withdrawing group on the dienophile. They're on opposite sides, aren't they? What does that mean about the deuterium? It's an inside substituent, so deuterium has to be this way. And the methyl isn't on the end. That's just going to be right here. So let's make sure we put that on the right place. 1, 2, 3. Because I messed this up in discussion, I don't want to mess it up here. Okay. So those would be the two things that we would combine to make that product. Questions on that one? Anybody? That is chapter 16. We're going to start on chapter 17. All right. All right, so what you might have noticed, maybe you didn't notice, but as you've been working problems all year, you might have noticed that benzene rings don't seem to react in any of the reactions that we've talked about. Right? They don't do the things that we did in chapter 10. They don't seem to react with anything. We have things benzylic reacting, but we've never really seen anything that's actually attacked the aromatic ring. And there's a good reason for that. So we're going to talk about that in this chapter. So what do we know about benzene? Let's draw the structure of benzene. We know that it's a resonance stabilized. So we can push these arrows around in a circle here. Resonance stabilized. We have two equivalent resonance structures. Two equivalent energetically. They're the same energy. Two equivalent resonance structures. So if we're going to draw a hybrid, it would look like this. Dotted dots in a circle. That's what the hybrid would look like. So you'll see in some textbooks where when they draw a benzene ring, they draw a circle in the middle. We're not going to draw it that way, but that's where that comes from that hybrid. All right, so in the resonance hybrid, 6 electrons from the 3 pi bonds are delocalized over the ring. The dashed lines mean that the pi electrons are shared equally by all 6 carbons. The dashed lines also indicate that all carbon-carbon bonds have the same length. So they absolutely do have the same length. This would be a typical carbon-carbon bond would be 1.53 angstroms. A typical carbon-carbon double bond would be 1.34 angstroms. And this is going to be something in between. And for benzene, all bond lengths equal. All bonds equal length. .39 angstroms. So somewhere between a single and a double bond in length. All right, so far so good. Hybridization in orbitals. This brings us back to chapter 1. All carbons are sp2 hybridized because all carbons are part of a carbon-carbon double bond. All carbons are sp2 hybridized. Therefore, trigonal planar. And bond angle is 120. All right, so and it turns out with benzene we have continuous overlap over all of the p orbitals. So if we draw benzene on its side, so this would be floating above your page, perpendicular to your page. And we know we have an unhybridized p orbital on every single carbon here. And what we have is continuous overlap on the top and the bottom. So when we were doing the NMR chapter, we talked about the fact that we have like a donut of overlapping electron density on the top and on the bottom, and we saw the consequences for that in the NMR. We saw that hydrogens that are bonded to that benzene ring are actually moved pretty far downfield because of that. So continuous overlap. Of the p orbitals. So kind of like a donut on the top and a donut on the bottom. All right, and you may have heard the word aromaticity or aromatic ring thrown around, but maybe you don't really know exactly what that means. Because we think of aromatic in 2 different ways, something Smells nice, you know, it's aromatic. We also think of it as, now you're going to think of it differently. In this chapter, it's something that's very, very stable. Okay. Questions so far? All right, so like I said, you know, we've just kind of, maybe in the back of your mind, you kind of noticed that benzene rings, they don't do any of the reactions that we talked about for alkenes. So we don't, when we do bromine, no reaction. Osmium tetroxide, no reaction. Hydration, no reaction. Ozonolysis, no reaction. Hydrogenation, no reaction. So it looks like we're not going to have very much to talk about, but we actually are, because benzene rings have their own different chemistry that's really separate from what we've already done so far. It turns out you can hydrogenate this ring, forcing conditions. Hydrogenation under forcing conditions. So 100 atmospheres of H2, this is done also in a bomb when you have these high pressures like that. Activated nickel is stronger than regular nickel. And so we can hydrogenate that, but it really doesn't want to be hydrogenated, which means it's really stable, right? If it's so hard to react with, you know, in reactions, then it's going to be really stable. And of course, no Diels-Alder with benzene. All right, so we know everything. Well, this is everything we know about benzene so far. And so the question we want to answer is resonance stabilization, is that enough to explain the special stability of benzene? And that's what we're going to try to answer right now. All right, so to answer this question, let's predict the expected resonance stabilization for benzene and compare this with the experimental resonance stabilization obtained when benzene is hydrogenated. And we'll see if we're right or not. Okay, so we have, in this first example here, we have an isolated alkene. One isolated alkene. And if we hydrogenate unsaturated molecules and they all go to the same product, we can predict their stability just based on measuring the heat that's given off when we do that reaction. All right, so one isolated alkene, we hydrogenate that, we're going to get this here. And the heat that we give off, we would measure this in a calorimeter, is minus 28.6 kcals per mole. If we have two isolated alkanes, and we hydrogenate two isolated alkenes, we still get the same product. Very convenient. So now we can compare stability. Delta H naught is equal to, we would expect 2 times minus 28.6. So if we have 28.6 for the first alkene, if we have 2 of them and they're isolated, we would just expect it to be 2 times that. And indeed it is. It's a minus 57.2 kcals per mole. All right, so now if we do the same experiment, except now we have conjugated double bonds. So this one here is whoa, what happened there? 2 conjugated double bonds. We know that when double bonds are conjugated, they're more stable, so we might expect this to give off less than 57.2. And indeed it does. So here's the product. Delta H naught equals minus 55.4 kcals per mole. So delta H naught for two isolated double bonds is 2 times minus 28.6 equals minus 57.2 kcals per mole. Actual delta H for two conjugated double bonds is minus 55.4. The difference is the resonance energy. All right, so we have a resonance energy for two conjugated double bonds is minus 55.4 minus a minus 57.2. So we want just the absolute value of the difference here. And that's equal to 1.8 kcals per mole. So that is the resonance stabilization for two conjugated double bonds. Questions so far? 1.8. We're going to put this all up graphically in just a minute. It will be easier for you to see what's going on. Okay, so on the next page, so now what do we expect for benzene? If two conjugated double bonds have 1.8 kcals per mole resonance energy, then if we add another double bond, wouldn't it be twice that? Would you expect twice that? Okay. Should have 1.8 plus 1.8. That's our working theory here. 1.8 plus 1.8 is 3.6 kcals per mole. And so that all we did to get that was we added another conjugated double bond. All right, so let's see what we actually get. Let's see if our prediction is correct. Again, we got to use forcing conditions. So we're likely not right in our prediction here. Notice extreme conditions. If it was just 1.8 kcals per mole more stable, we wouldn't have to use activated nickel in 100 atmospheres of hydrogen. Okay, so let's see what we actually do get. Delta H naught equals minus 49.8 kcals per mole. Expected delta H naught for three isolated double bonds is 3 times minus 28.6. That's equal to minus 85.8. We are very far away from 85.8. Actual is minus 49.8. So the actual resonance energy is the absolute difference of the absolute value of the difference between these two guys. So whatever you want to put up first, it doesn't really matter here. I suppose I should do it the other way. Minus 49.8. We'll just do a little absolute value here because I should have switched that around. Can't have a negative number for resonance stabilization. 36 kcals per mole. By adding simply adding another double bond there, we have 36, 10 times what we would expect. Okay, so something's going on here that we can't explain with simple resonance stabilization. So here's what we actually have here graphically. What we're doing is we're hydrogenating each of these. So they're all going to the same product, cyclohexane, and that's the energy for cyclohexane. We start here with one double bond, releases minus 28.6. Two isolated double bonds, twice 28.6. Now we have them conjugated. We'd expect minus 57.2, but it's actually a little more stable. It only gives off minus 55.4. So this is at a lower energy. And now we would expect here, all the way up here, and this is actually lower than both of the two of these. Okay, so there's a really big thing going on here. So the difference between the actual and the expected. It's no wonder this thing is not very reactive, because it's really, really stable. Now, and just to give you an example of how this is very different here, we have, let's just compare this guy here. This guy here, we have 3 conjugated double bonds. What is the resonance stabilization here versus benzene? And the resonance stabilization here is 3.6, just what we expected for benzene, kcals per mole, and this is 36 kcals per mole. So what we would call this is unusually stable. It's unusually stable, and we can't explain why it's so stable just using resonance. It's not adequate enough explanation for the 36 kcals per mole. So are you impressed with the stability of benzene? If you weren't before, maybe hopefully you are now. All right, so maybe are you kind of thinking this little idea in your head, maybe the ring has something to do with it? Right? Maybe it has to do with maybe there's something magical about that ring. So that maybe we're all thinking that. Let's see if we're right on the next page. Maybe the ring's got something to do with it. All right. So if resonance stabilization were the only reason for benzene stability, we might expect similar, that is what I just got through saying. Are similar conjugated systems unusually stable? Let's answer that question. Cyclobutadiene, 2 conjugated double bonds in a ring. And what we're going to do here is we're going to count pi electrons, because benzene has 3 double bonds. How many pi electrons? 2 for each, 6 electrons. We're going to count pi electrons here. So I want you to kind of try to look for a little pattern here. You're going to have a hard time finding it, but this would be 4 pi electrons. 2 for each double bond. This would be benzene is 6 pi electrons. Cyclooctatetraene, 8 pi electrons. Cyclodecapentaene, 10 pi electrons. And then we jump all the way down. Nothing happens in between 10 and 18 aniline, which has 18 pi electrons. All right, so here's our idea here. The ring has something to do with this. Let's see if these other guys are especially stable. And we're going to quickly be frustrated here because cyclobutadiene has never been isolated and purified. The only way we can actually know that we can make cyclobutadiene, it's prepared at low temperature, extremely low temperature. Prepared at low temperature and trapped in frozen argon. And that's what you do when you want to make really unreactive molecules that you can't see at room temperature. You trap them in frozen argon. Sounds horrible, doesn't it? What temperature would frozen argon be in? Does anybody know that? I know it's really low. Does somebody know? Any of my TAs know? I think it's like, I want to say like minus 178, something like really, really cold. So I'm sure that you would all agree that this is extremely unstable. Okay, so that goes that idea. We know 6 pi electrons has unusual stability. And really the number matters here. 8 pi electrons, no special stability. So benzene's really starting to look pretty magical here. No special stability. It reacts like a normal polyene. So that that means it'll do reactions like we did in chapter 10. Addition reactions, you could add bromine, you could add bromine water, things like that. Cyclodecapentaene, 10 pi electrons, also no special stability. Reacts like a normal polyene. And what happens is when we finally get up to 18 annuline, we also have unusual stability. All right, so let's see what's going on. We already know that conjugation is not enough to explain the special stability of benzene. Our ring idea seems to be out. But not completely, because the 18 annuline also has unusual stability. So our conclusion is there must be something more than typical resonance to stabilization to explain benzene's extraordinary reactivity. And it turns out that there is an explanation, and it has to do with molecular orbitals. And I know you guys love molecular orbitals, right? I'm going to make this as simple as possible. We're going to draw the molecular orbital picture for benzene, and we're going to actually be able to see why benzene is so stable. How on earth do we draw the molecular orbital picture for benzene? And it turns out that it's not that difficult to do, and you do something called frost circle. When you have a ring where all of the bonds are, all of the atoms are sp2 hybridized, you can use frost circle to draw the molecular orbitals. So you're going to draw the cyclic compound with one of its vertices pointing down. I'm going to draw benzene really big here. So the vertice is where the two bonds cross. Relative energies of the pi molecular orbitals correspond to the relative levels of the vertices, and molecular orbitals below the midpoint are bonding, and molecular orbitals above the midpoint are anti-bonding. So every one of these vertices is a molecular orbital. And here's the midway point. So just draw a dashed line through the midpoint here. Above this is anti-bonding. Below the midpoint is bonding. So above the midpoint, these are all the anti-bonding molecular orbitals, and below the midpoint is all the bonding molecular orbitals. How many anti-bonding molecular orbitals do we have? There's 3, right? Each one of these lines is a molecular orbital. 1, 2, 3. What do we call it? These two molecular orbitals have the same energy. What do we call that? Degenerate, right? So these are degenerate, but they are separate molecular orbitals. These are degenerate. We have 1, 2, 3 bonding, and we have 1, 2, 3 anti-bonding. All right, so what we're going to do is we're going to combine 6p atomic orbitals. So remember, when we make molecular orbitals, we combine atomic orbitals. And however many orbitals we combine, we get that many molecular orbitals. So if we combine 4 atomic orbitals, we get 4 molecular orbitals. If we combine 6, we get 6 molecular orbitals. So we're going to combine 6p atomic orbitals, each with 1 electron. What is the energy of those p atomic orbitals before they combine? This is before they combine. It would be this energy that's right in the middle here, this midline here. That's 1, 2, 3, 4, 5. We need 1 more. So we combine 6p atomic orbitals, we get 6 molecular orbitals. And that's exactly what we have. All right, so far so good. Now, we have, so each has 1 electron, so let's fill up these orbitals. We have 6 electrons altogether, right? We fill up the lower energy first and we pair the spins. This goes all the way back to chapter 1. Degenerate orbitals, we put 1 electron in each first, and then we go back if we have more and we pair the spins. So that's 1, 2, 3, 4, 5, 6. And it turns out that this configuration with all bonding molecular orbitals filled, which we call a closed bonding shell, is energetically very favorable and accounts for the special stability associated with aromaticity. There are other numbers of electrons that correspond to filled shells for smaller and larger rings, and that leads us to Huckel's rule. And we're out of time, so we'll save the Huckel's rule till Friday.